So in the last video, we looked at the normal light reflex pathway, and we can recap that now. So say if we were to shine a light in the left eye here, the retina would send fibers to the pretextual nucleus, and that would stimulate both the ipsilateral and contralateral endogo-westphal nuclei, thereby stimulating the efferent pathway, a parasympathetic response to cause constriction of both eyes, the consensual reflex. So that's a positive direct consensual pupillary reflex. Let's just redraw that. Okay, so say if we were to have a defect in the afferent pathway. So remember, the afferent pathway runs from the retina to the endogo-westphal nucleus, and if we were to have a defect in that pathway somewhere, then what would happen? Well, if we were to shine a light in the left eye, then there will be no stimulation of either endogo-westphal nuclei. There will be no stimulation, therefore, of the efferent pathway in either the left or the right eye. So you wouldn't get any constriction. You'd get no constriction of either eye. However, if you were to instead shine a light in the right eye, but still have that defect in the left eye, in the left afferent pathway, you would still be able to stimulate constriction of both the left and right eyes, because both the endogo-westphal nuclei are parasympathetic fibers can be stimulated from there, cause constriction. So what we've just talked about, that is called the afferent pupillary defect, a complete afferent pupillary defect, a lesion there. So anywhere from the retina to the endogo-westphal nucleus is a complete afferent pupillary defect. And that can be caused by numerous things. It could be a retinal artery occlusion, it could be a retinal detachment, amongst other things. Now, the next thing we're going to look at is what we call the relative afferent pupillary defect, or rapid. And that is where you may not have complete blockage of a pathway, of the afferent pathway, but it may just be damaged, or there may be some demyelination or inflammation, whereby that means that impulses traveling through the afferent pathway are reduced and may not work as well. And that can be caused by for example, optic neuritis is the classic example, affecting the optic nerve called the chiasm. So how would that look? So I've rewritten, well, I've got an image here, a simple flowchart, very similar to the one we just looked at. So it's the same diagram, so retinal ganglion cells, pretextual nucleus, to endogo-westphal nucleus, and then reach the ciliary ganglion and then pupil constriction. So what's illustrated here is that, say if this is the left and right eye, again. Now the left eye is affected. It's not got a complete afferent pupillary defect, but there's a relative afferent pupillary defect, so the impulses are slower and they don't work as well in that eye. So that would mean that if you were to shine a light in the left eye, there would still be constriction, but there'll be less, and therefore the consensual reflex will also be less as well, because remember that both endogo-westphal nuclei are stimulated from the pretextual nucleus. So how will that look in terms of pupil size? So let's assume we don't know which lesion the relative afferent pupillary defect is in. So this is what we call the swinging flashlight test, which we use. And swinging flashlight test means that, so initially you start with one eye and you shine the light in that eye for 3 seconds. So let that eye acclimatize. And then you need to quickly, so this is what we've done, we shine a light in one eye, and in this instance, both pupils have constricted. So that means this eye, the right eye's afferent pathway, must be working fine. must be working okay. So that must be the normal eye. So once we've shone the light in the eye for a good 2 or 3 seconds, we then quickly change the light to the left eye. And notice how in the left eye, both pupils are dilating. And that's abnormal, that can't be right. So therefore the relative afferent pupillary defect, must be in the left eye. And then it's good to swing it back to the other eye again. You can see that's the normal response in, and the right eye is okay. The afferent pathway is okay. So this is where, so the lesion is in the left eye. And the relative afferent pupillary defect is also known when you see that pattern, is also called a Marcus-Gunn pupil. Marcus-Gunn pupil. So that's how you detect a relative afferent pupillary defect. Last thing to note, I'll get this back in focus. What about an efferent? What if you had a defect here? So defect here, that would be called an efferent pupillary defect because it's after the ending of Westphal nucleus. And that usually affects the postganglionic fibers running from the ciliary ganglion to the sphincter pupillae. So if you were to shine a light in the left eye, the constriction would not occur in the left eye because of the lesion here, but you would still get constriction in the other eye. And if you were to, let's do that again here. Say if the lesion was there again, but you were to shine a light, shine a light into the right eye, again you can see the constriction doesn't happen in the affected eye. So in an efferent pupillary defect, there is constriction. Constriction does not occur in the affected eye at all, whether you shine it in either. So that concludes this video on pupillary defects. We'll look a bit more at anisocoria, which is unequal pupil size, in another video.